Dr. Andrea Mammoli. Then I'll give the presentation. I'll hand it over to Dr. Mammoli. So hello everyone. So welcome to the current power and energy seminar series of today. So if you students, if you register for this class, make sure that your name is showing up correctly, because I'm taking attendance based on the name that you're showing here. So if you have questions during this presentation, you can either type your questions into the chat box or raise your hand so that I can unmute you at the end of the presentation. So today we are glad to have Dr. Andrea Mammoli from EPRI to give a presentation entitled Inexpensive Thermal Storage at the Smaller Scale. Dr. Andrea Mammoli is Principal Project Manager in the Customer Technologies Program at Electric Power Research Institute and area lead for Project SETX, Tools and Technologies Development. He leads projects ranging from development of innovative near-zero GWP heat pumps for CEC to deployment of AI to detect equipment degradation using AMI data. Prior to joining EPRI in 2019, Andrew was professor of mechanical engineering at the University of New Mexico and director of the Center of Emerging Energy Technologies. During more than 2 decades spent at UMN, Andrea led research in complex fluid at row Reynolds numbers, solar thermal energy systems, building energy management and optimization, and finally design of microgrids focusing on the community scale. Andrew obtained his Bachelor of Engineering in 1991 and Doctor of Philosophy in Mechanical Engineering in 1995 at the University of Western Australia. He subsequently spent 2 years at Los Alamos National Laboratory as a director's postdoctoral fellow before joining UMN. He is currently on the editorial board of Energy's Journal and has authored over 150 peer-reviewed journal and conference papers. Thank you, Dr. Andrea Mammoli, and let me turn the presentation to you.
Great, thank you, Hantel. Good morning or afternoon, everybody. And I'm glad you can attend this talk, and I hope that you enjoy it. So let me see. Okay, let me turn on the slideshow here. Hantel, can you see this?
Yes.
Okay, great. So thank you for the introduction. And so I've been with the Electric Power Research Institute for a little bit over a year now, after a couple of decades at the University of New Mexico, and I did a lot of projects there that involved energy systems at the building scale, at the power distribution scale, and so on. And then, I decided that I needed a change, and I wanted to see what the industrial side of things looked like. And so, as you're probably aware, EPRI is let's say the research arm of the utility industry, and we're a nonprofit research organization, and our charter is essentially to enable or to assist with providing society with clean, reliable, and affordable power. So what I'm going to be talking about today is thermal storage at the smaller scale, and by smaller I mean at the residential scale. So, okay, so ice storage, or thermal storage, but particularly ice storage, has been around for a long time, and so I always wanted to, cite the Bible in my references. So here you go. It's, they were talking about ice storage, ice thermal storage since a long time ago. Even, the Romans actually used. There are records of the Romans using snow to cool down air inside of buildings, and then a lot of stuff happened over history. More recently, we have in the 1800s, there were various kinds of cooling systems, mostly having to do with blocks of ice, and you basically move air through tortuous channels inside these blocks of ice, and as air moves inside the ice, it cools down, and typically also acquires a little bit of moisture, which is not necessarily a good thing. Ice storage has seen ups and downs over the years and over the decades. Before mechanical refrigeration, ice storage was basically the only way to cool buildings. Again, people were using all kinds of strategies for extracting or for extracting cool out of ice, including by circulating water over ice and then using the chilled water to circulate through heat exchangers and so on. But then in the early 1900s, there were two things happening: the advent of electricity that allowed motors, as well as refrigeration systems, basically compression cycle refrigeration. And so ice systems declined in use. People were still selling ice in large blocks to put in cold rooms at houses to keep food cold. So I don't know how many of you are aware, but the unit of refrigeration to this day is a refrigeration ton. And basically what it means is that it's the equivalent refrigerating power that you get if you melt a ton of ice, literally a ton of ice, over the course of a day. So that's what a refrigeration ton means. So anyway, so ice systems, their fortunes went up and down, throughout the 1900s. In the late 1900s and the 1970s, there was an energy crisis, and so people were trying to make things more efficient. So one way to make things more efficient in refrigeration systems was to use a cooler cold sink, which is essentially the atmosphere at night. So you basically generate ice at night and melt the ice during the day to cool spaces. Right. Also, the utility industry saw benefits in using ice because they could say, hey, we've got a very low load at night. We want to keep our plants running at as much of capacity as possible. I'm sure you guys are all aware of this. And so this is our base load. We want to use as much of our base load as possible. So let's make a bunch of ice, and then let's reduce the peak during the day when it costs a lot of money to make electricity. So customers were taking advantage of low rates, off-peak rates, to make ice, and utilities were able to sell power off-peak. So everybody was happy. But this worked pretty well at larger scale. So you can see here the picture on the right is CalMech ice banks. They're big tanks that are like 3-4 meters in diameter, 3 or 4 meters tall, and they're full of plastic coils that circulate glycol, and they're immersed in basically in water, and you freeze the water, you make ice. So this is a typical ice and coil system. So today the context is different, right? Because off-peak and on-peak is with increased renewable energy generation, this is taking on, it's looking different. Okay, so off-peak today means a different thing from what it meant, even 15 years ago. And also, utilities are looking at different pricing schemes. So instead of time of use, they're looking at real-time pricing. And so, what you can do with storage, it may look a little bit different from what it looked like a little while ago. Okay, so we large-scale ice storage. It's been around. It's not a huge part of the industry, but it's still there's still a considerable market for it at the commercial scale. But residential is still not around, and it's really never been able to break the market barrier. And why is that? Well, so for the majority of customers, tariffs do not encourage reducing peak demand. So basically, I'm going to run my air conditioner when I need to run it, because I pay for the electricity just the same way at night as I do during the day. This is not necessarily true anymore in some markets. Like California, for example, is getting big time into time of use rates, even in the residential market. But there are choices still. So you can buy energy or you can buy power at different times. Also difficult to build. This is a technology that essentially is more cost effective at larger scales. Just like power generation is more cost effective at larger scale, or at least historically, that's the way that it's been. Customers don't want to add complication to their appliances, because the more complicated they are, the more they break. They don't want to pay for a storage system, because where are the savings? How long is it going to take to pay back? And also, people will buy a PV system, right? Because you can see it on your roof, and it's green. It's all these things. A nice storage device that sits in your garage. First of all, you don't necessarily always think of it as a green thing. Secondly, you don't see it. It sits in your garage. It's it's like, blah. Why do I need it? But there are reasons for thinking about these things. So let's look at peak demand. So this is actually a fairly old pie chart from California Energy Commission. But today the percentage of peak load that is due to air conditioning may be even larger. But even in 2001, air conditioning was 40% of the peak residential load. Okay, so that's by far the biggest slice. And so why do we care about that? And today, with climate change, with the heat waves that we've seen just even in the last couple of months in California, and we're going to see another one next week, this becomes an even bigger problem. Okay, so what's happening in today's context that makes things even more important? So I assume, even though I can't see you, but I assume that most of you are familiar with the California duck, the famous duck curve. So if you look at the net demand on the distribution grid as a function of time of day. So in 2012, it was there was some morning peak and some evening peak. As people put in more and more rooftop solar, the net load goes down when the sun is highest up in the sky, when solar generation is highest, and the more that people install solar on their rooftops, the bigger the belly of the duck becomes. So basically, at some point in the middle of the day, sometimes the California power system has to turn down a bunch of generation resources. All their gas generation gets turned down, but sometimes you need to turn off things that you don't necessarily want to turn off, because it's a problem for the system to turn on power stations that are designed to run at peak full time. Also, at the end, so in the late afternoon, sun goes down, everybody comes back home, and turns on their air conditioning, turns on their appliances, and you see, so the neck of the curve here, I don't know if you can see my cursor, but so we have a big ramp in electricity consumption. And so all these units that had been turned down in the middle of the day, all of a sudden have to rush to get back online at full speed. And then you have this evening, very pronounced evening peak, like the head of the duck, where basically you've got all your generation that sits almost idle for much of the day, and you've got to run it at full speed. That's also not a good thing. So this is just on the micro scale. This is how, what generates a duct. And, basically these are actually compressor speeds for a number of we're doing a project here at EPRI. We're monitoring the power of a number of customers' heat pump compressor speeds, and you can see the same thing, right? So basically, you have a morning peak, and you have not much happening in the middle of the day, and then you have an afternoon peak again. So so this is part of why there's a morning peak and an evening peak, and so the concern is, can we make this thing more uniform? Can we run these things in a more evenly distributed way throughout time? And why does this matter? Okay, well, so here are some things that we saw last month in California, highlighting the problem. So in the middle of August, about a month ago, so we had a heat wave in California, and but things were looking okay. The system operator was they had planned for it. They knew the forecast, and so they were going to be able to run things pretty well. Except that at some point, a big 400 megawatt gas plant failed, and right after that, another gas plant failed, 450 megawatt gas plant failed, and then in combination with that, the wind dropped off rather, wind generation dropped off rather unexpectedly. And so so you can see, this is, I don't know if you can see my cursor, but this was the forecasted load at 49 gigawatts, almost 50 gigawatts. And all of a sudden, they did not have the generation capacity to meet that. At the same time, they were going to import power. This is what California does. It imports power from from Arizona or from the Bonneville Power Authority up north, but everybody else was going through the same heat wave, so they did not have any spare capacity. So basically, they were running short on reserve capacity, and again, as you probably know, you need to have a little bit of reserve capacity in case something else happens that's unexpected. Because otherwise, if the system goes down completely because you're totally out of capacity, it can take days or even weeks to bring it back up. So they didn't want to do that, and so they ended up doing a series of rolling blackouts, and these rolling blackouts hit people that really needed electricity because they were in the middle of a heat wave, and hospital houses with elderly people and all these things. So basically you're cutting off power right when people need it the most. So that's not a good thing, right? So there's got to be something we can do about it. So again, air conditioning is a big chunk of the peak load. And so if we can move it to some other part of the day, like when you have a valley instead of a peak, you can survive these things a lot better. So, all right, well, so I don't know how many of you are familiar with the ice bear. This was a small commercial scale technology. So this is basically cooling, ice storage, not necessarily for hotels, but let's say for strip malls and box stores and so on. So this was a company, Ice Energy. It's been around for a couple of decades, and actually, as it turns out, a year ago, more or less a year ago, they finally went bankrupt. But anyway, they had this interesting system. It was an ice on coil system. So basically, it was a box full of water with a bunch of copper coils that contained refrigerant, and so you would run cold refrigerant through the coils, freeze water, make ice, and then use it later on instead of running your compression cycle. So, but this was still rather expensive technology. So a nice box like this would typically cost maybe anywhere between $10,000 and $20,000 for a house. So basically, as much as your air conditioner. And it was not terribly successful at the residential scale. So the question is, can we make it a lot cheaper than that? So I guess the genesis of what I'm going to be talking about today is this was a Solar Decathlon entry in 2013. There was a collaboration between Arizona State University and the University of New Mexico. It was called the Shade House. And, I don't know if you're familiar with Solar Decathlon, but it's a competition where students and faculty design and build these 100% solar houses that then compete against each other for all kinds of things on the National Mall. And so, we entered the competition. We did a little bit better than Texas, which is what we, we didn't win, but we did better than Texas. So anyway, one of the components of this house was an ice storage device. And in fact, the ice storage device was called the TherMech. And the concept is basically, it hinges on low-cost materials. So here's how it works. You basically have a container that has individual channels. So these light blue channels, and they're made of corrugated plastic, right? So basically, the stuff that you use for advertising signs or election signs or things like that. Okay, interleaved between these channels, you have polyethylene bags that are filled with water. Again, just like a hot water bottle. Hot water. What do you call those things? Like a hot water pillow type of thing, except that it's designed to hold ice, and so the concept here is you flow a cooling medium. It enters at the bottom. It's below the freezing temperature of water. It runs through these channels, and it is in contact with the water bags. And it freezes the water in the bags. Now, the main concept here is that there is a lot of surface area. Okay, so basically, the idea of the system, the main idea of the system is that because you've got these fairly thin layers of cooling medium, water ice, cooling medium, water ice, interleaved between each other, a lot of surface area. That means that you can have very effective heat transfer. Okay, so that is the key component. And the other key component is inexpensive materials. So here are the materials themselves. Okay, so I mean, the container can be made with very low cost technology, just like basically an ice cooler. The channels can be made of corrugated plastic. Bags can be made of polyethylene. And of course, this is something that you would make at home, right? If you made it in an industrial way, you would probably use slightly different means, but this is how we built it in the lab. And then, glycol. So not very expensive, right? Okay, so what is the actual system? I'm going to show you a cartoon of the system. So, so now we're trying to charge the system, right? So the components are fixed in their position. The only difference that that exists between the different modes of operation is the valves, right? So you basically switch the flow of fluid and the direction of flow by switching these valves around. So in charge mode, the green valves are open, so you basically have water flowing in a clockwise way. So here's a pump. It flows inside the heat exchanger through the green valve, through the bottom of the ice storage device, which is this blue and red box. This is cold heat transfer medium, so it's going to be a glycol water mixture. It sees these the black lines. These are the ice bags, and it starts freezing them, right? So it starts freezing them, from the bottom, and so the freezing front moves from the bottom up all the way, and then so the heat medium warms up as it contacts the water and freezes it and makes it into ice, and goes through a heat exchanger. This is air to glycol heat exchanger. but there's nothing happening here. There's no air circulation, so there's no heat exchange in the heat exchanger. It just goes through it anyway. It goes back through the pump, and the cycle begins again. In this heat exchanger 1, this is a heat exchanger that comes from a chiller, right? So you basically have an air conditioning unit on this side that provides cold refrigerant. So this blue arrow here is cold refrigerant, and it serves to cool back down the heat transfer medium. Okay, so basically the source of cool is a heat pump right here, and it goes to the storage, and it freezes the storage. Okay, so this is charge mode. In discharge mode, you basically switch a few valves around, and what do you do in discharge mode? You are taking the cold from the ice storage, and you are routing it. Okay, so it goes, you see here, so water flows from top to the bottom. It flows through this valve B3, goes to the heat exchanger HX2. So this is basically the heat exchanger that cools down the air that goes to your house. Okay, so the air, warm air, return air from the house, goes through the heat exchanger, cools down. It warms up the heat transfer medium, which then goes to the pump, goes through the heat pump heat exchanger, which at this moment is not doing anything because it's we're using the cold from the ice storage. So it goes through here, and so nothing happens to it in the heat exchanger, just goes through it, and then goes back through B4, and then back down through the heat exchanger. And so as time progresses, this red area, which is, let's say, the thawed area of the cold storage, moves further and further down. Okay, so the freezing front, let's say, moves down all the way until you've discharged it all the way. Okay, and then there may be some cases where your storage is discharged and you just want to bypass it, and so again you operate some valves, and so now you're using your heat pump to provide cool to the heat exchanger. You're cooling down your heat medium, and you are cooling down the air in your house by using the heat pump directly. Okay, so this mode of operation is basically just using your air conditioner normally. Okay, so let's do a little bit of mathematical modeling. I'm not going to go in too much detail through the equations, but just wanted to show you how I actually simulated the process here. So, I mean, intuitively, this is what happens. I hope that you can see the cursor in my picture here, but basically, so you have cold glycol flowing through these channels, so these big black arrows, okay? So you've got very cold fluid on both sides of your ice pack, and so what happens? Basically, you have a cold surface, so you have freezing that starts from the side, and it moves inward, and then you have a freezing front that is going to have some kind of a shape, like in the drawing here. So basically, it's going to be frozen. It starts freezing at the edges, and then it catches up at the middle, and the freezing front proceeds further at the edge, and then the middle catches up, right? So basically, what you're doing is you're making ice, and ice. The ice making starts at the bottom and eventually during the charge process, the ice front moves up until it's all frozen. Okay. When you're discharging, it's basically the opposite thing. So you've got warm heat transfer medium, and it's warm because it has just cooled down the air, and it warmed up in contact as it contacted the air. And now you're trying to cool the heat medium back down, and you're doing that by melting ice. So now you've got a melting front, right, instead of a freezing front. And again, you're melting ice from the edges in, okay, and the melting front is moving downwards in this case. Okay, so that's the intuition. How does that really look like? And the way that we figure it out is we do some calculations. So this is the numerical model that I set up for this. So basically, we have on the top, the purple there is the heat medium. So this is our glycol water mixture that flows from the ice storage to the various heat exchangers, to the air heat exchanger to cool down the air, and then through the heat pump heat exchanger to get cooled down again. Okay, so basically we have so we're assuming that the bulk temperature, that the temperature is, so we're modeling the bulk temperature in this purple area at various nodes. So the variation in temperature is only in the horizontal direction. Okay, so basically we're looking at the temperature evolution through these nodes, I-1, I+1, etc., and they're spaced equally at a distance delta x from each other. And I promise there's only a couple more equations here. Now for each one of these nodes, we have to model the evolution of the we have to model the formation of ice in the water. Okay, so this control volume is basically where you are either melting water or freezing water. Okay, and so there's going to be a temperature profile which is also modeled by a series of nodes. Okay, so we're doing a finite difference formulation. Okay, it's a coupled finite difference formulation. All right, so for the convection in the heat medium, okay, this is your typical equation. So the temperature at node I at time p+1 is equal to the temperature at node I at the previous time step plus the heat transfer that occurs because there's a temperature difference between the temperature of the surface and the bulk temperature. Okay, and this is these are basically geometric parameters. U is your heat transfer coefficient, mass flow rate, heat capacity, etc., etc. It's usual stuff that you see in a heat transfer equation. Okay, so nothing extra fancy there. Okay, and the correlation for calculating the convection coefficient can be found in this old paper that I had to dig up from 1971, but it's there. And that's the convection part. The conduction in the ice is interesting. Conduction is interesting because you have two phases, right? You have an ice phase with one set of characteristics for the fluid, because ice has different thermal properties than water, and you have a water phase. Okay, and it's only conduction because the assumption here is that there is not a whole lot of fluid movement. Okay, there's no natural convection processes in the water. Okay, and you basically set up, this is your typical finite difference formulation. Okay, so again, nothing fancy here. It's basically an Euler explicit calculation, and this is the finite difference version of the heat equation. Okay, so I don't think I need to get into it, but this is basically time derivative of temperature at some node. Let's take central nodes. Okay, time derivative of temperature, and this is the second derivative of temperature with respect to position. Okay, again, this is the finite difference formulation of the heat equation. I hope that you're all kind of familiar with it. It's kind of a mechanical engineering thing, but I'm sure that electrical engineers know it too. Okay, so basically what do we do here? So we're transferring some energy from the heat medium, right? So this is the convection equation in the previous slide. So this guy, right? We're transferring some of this energy, and we are using this energy to modify the temperature profile of the ice region and the water region. Okay, now so there's going to be, to move from the solid line to the dashed line, it's going to take some energy. Okay, here again, to move the temperature profile from the solid line to the dashed line, it's also going to take some energy, and the energy that is left over from that is gonna be what is left to freeze the water. So basically what's happening here is we are moving, so we're freezing water, right? We're making ice, and we are moving the boundary where the ice is. So this red dot is the position of the ice interface. Okay, now I hope this is making sense. If it isn't, there's actually a full paper in applied thermal engineering that I can point you to. All right. Now, so there's only one small numerical consideration that you got to take into account. So as those of us who do finite difference calculations every now and then know, there's a balance between the time step that you can use and the size of the physical discretization. And so as your physical discretization gets smaller, the time step has to get smaller by a factor of physical discretization squared. Unless you use an implicit Euler formulation, which is implicitly stable and it's not going to blow up on you. And so this is what we did here. So for this node, when we have a nice front that is very, very close to the edge, so we use a special equation, we use an implicit formula. And the reason why we can use an implicit formula here is that this guy here, so implicit means that you're using the temperature at the next time step, right, as opposed to in your finite difference formulation. So now the thing is, so theta 2 here is the temperature of this red dot, and because this is the ice front, we know that this temperature is, because it's in equilibrium, it's at the interface between ice and water, so we know what this temperature is. It's 0 degrees C, okay? So then we have one fewer unknown in our equation, and we can actually write an equation for it, and lo and behold, it actually works pretty well. So this is solidification at just one of the temperature stations in my ice profile, and you can see here. So okay, we have temperature here on the z-axis. We have z position. So basically, this is the interface with the heat medium, and this is the center line of the ice bag. And here is time. Okay, so basically, as we start cooling the interface between water and ice, we can see that initially we have sensible cooling, then we start freezing, right? So this is where you see a change in slope. This is where the freezing begins, and then you can see the temperature. So basically, what you're doing is you're pulling down the temperature of each of the internal nodes as time goes by, so essentially you're extracting heat in out of this surface, right? And you're depressing the temperature at the edge of this surface here. And by depressing this temperature, you eventually, by conduction, bring down the temperature through the rest of the field. Unfortunately, it's kind of hard to illustrate that with my cursor here. If I was in a live situation, I would kind of hand wave and do all kinds of things. But I hope that you're sort of following that. So, all right, now, okay, that's the end of the equations, right? So what's our competition here? I mean, you can do storage with batteries too, right? So why are we focusing on thermal storage? So here's the competition. This is I apologize. This is a Tesla from a few years ago. It looks a little bit different now, but more or less has this very similar properties. So in this case, it was a 6 kilowatt-hour electricity capacity for daily cycle applications. It had a maximum power rating of 2 kilowatts continuous, 3.3 kilowatts peak, right? 92% round trip efficiency. Can charge it from photovoltaic. Can cycle it 5,000 times. 5,000 times. So if you do it every day, if you cycle this battery every day, that gives you what, about just over 10 years, right? So that's not too bad. Costs you about $3,000 to purchase. So it's $468 a kilowatt hour and $1,500 a kilowatt. Okay, can we compete with that with a thermal system, right? So what should we do? So the thermal equivalent of 6.4 kilowatt hours of electricity storage is, if you include the coefficient of performance of a typical heat pump, about 19.2 kilowatt hours. Okay, so 207 kilograms of ice. So that's the size of, let's say, a relatively small, like refrigerator, like a bar refrigerator that you would find in your hotel, right? So we have to provide the equivalent of 2 kilowatts of electricity demand, right? So basically a discharge capacity of 6 kilowatts, right? So this is a thermal capacity of 6 kilowatts. So that's what we're going to use for our calculation. And, it has to last over 13 years. Can a thermal system last 13 years? Well, yeah, probably, yeah, because it doesn't really degrade, right? In fact, thermal systems like this, if you look after them properly, they can last 20, 30 years. Okay. A little bit of results from so these are numerical results from my simulation. And just here I want to show you the shape of the ice front. Remember, we assumed that it was going to look a little bit like well, it was going to freeze from the edge, and it was going to be liquid in the middle. And this is exactly what's happening, right? So basically, the green line here is the interface between at some instant in time, 6,660 seconds. So this is the shape of the interface between water and ice, this green line. Temperature of the ice is at the same temperature as the cooling medium, which I set to -2 degrees, right? So there's just again, we want to minimize exergy destruction, right? So we want to keep temperature differences fairly low. So, a 2 degrees C, a -2 degrees C heat medium can freeze ice fairly effectively because of the large surface area, right? So, this green line here would, kind of move in this direction as time proceeds, okay? And okay, so here's a time evolution of the temperature profiles. Okay, so this is the temperature at the interface between the cooling medium and the ice, right? So we start off with, this is the beginning of the simulation, start off with fairly large temperature differences as cold heat medium meets, water at its initial temperature. It depresses the temperature of the water, but it acquires heat, and so eventually it achieves equilibrium. So basically, this area here, where the blue line and the green line are different, this is where you can transfer heat, right? When the temperatures are the same, no more heat transfer, right? But so as time evolves, you basically bring down the temperature of the water, and the delta T, the finite delta T, moves further along the ice pack, and as you can see this evolving through time. Okay, so this is at 100 seconds. This is, this is after a little bit less than 2 minutes after you start the system. Anyway, so you can see a lot happens at the beginning, and then things kind of settle down. You have relatively small temperature differences, and eventually you start freezing. So here's where freezing starts, right here. Okay, and so you can see that you basically have this relatively small delta T that moves from the entrance of the ice pack, and then as time progresses, it freezes ice, and the temperature difference moves to the let's say the end of the ice pack here. Okay, when this delta T moves all the way to here, then you're done freezing because you've run out of water to freeze. Okay, so basically this area here, this cliff edge here, is where freezing happens. And this is time evolution of heat flux profiles. Okay, I guess I'm almost out of time here, but so anyway, you can see that heat flux profiles change. You have very high heat flux until, so this is early on. This is the area of interest. This is where you're freezing ice. So basically you have relatively constant, see, this is constant heat flux all the way until you have completely frozen your ice pack. Okay, and that's what you want. You want constant, because that's what you can do with a battery, right? With a battery, you can extract power at a constant rate, and that's the same thing that you want to do with an ice pack. You want to be able to deliver constant thermal power from the beginning, from when you start using the device to the to when you're done. And in fact, so here you go, right? For for about, what is it, about 3 hours. You charge your system. So you have a 6 kilowatt. Remember, we're competing with a 2 kilowatt electric, so that's about 6 kilowatt thermal. And so you're transferring heat at a constant rate until you run out of stuff to freeze, and then you drop off pretty quickly. Okay, so what are the outcomes so far? Well, the numerical method works pretty well. Solidification front develops as expected. You can charge the device at maximum compressor capacity for a good portion of the time, right? So that's one thing that you want from a storage device. You want to be able to charge it and discharge it at a constant rate. That's important, and that's what most of the devices that are commercial, ice on coil devices. That's what they cannot do, because basically, as they operate, they start building ice around the heat transfer, which is typically a coil. It's a pipe, and as you build ice around the pipe, ice has a lower heat transfer coefficient than water, lower conduction coefficient than water, and as a result, as you build more ice, you're less able to transfer heat effectively. Here, because of the way that we designed the heat transfer surfaces, you've got a constant rate. All right, so again, melting, this is melting, right? It basically looks the same way as charging, just in the reverse direction. So I'm not going to belabor this, but okay. So in the discharge, this is where constant is important. Okay, so you want to discharge at peak rate for 2 to 3 hours. Basically, you want to hit the head of the duck with a hammer. Okay, that's kind of cruel, but anyway, squash it, because that's where you have your biggest problems with peak capacity, right? And so, can you do that? Can you take a system like this, discharge it at peak rate for 2 hours? And okay, again, evolution of the temperature profiles, if you're interested in the details, and you can stare at this diagram for a little bit, but so anyway. The interesting stuff happens here. Okay, again, you've got your melting front now, and as time goes by, it basically stays the same. It occupies a different portion of the ice storage device, space-wise, but it essentially looks the same. It's got the same delta T's, and it discharges at a constant rate. Okay, so heat flux surfaces. Okay. But here's the important thing, right? So we can actually transfer heat at 10 kilowatts thermal for what is it? Just 2.5 hours. Okay, constant all the way, and then we run out of ice, and we've got to stop and recharge. Okay, so how much does this thing cost to build? Well, all right. So these are the components that you're gonna need, right? So you need a raised place heat exchanger, $172. Okay, so I sized it for the equivalent of 2 kilowatts electric. So basically, what a heat pump that draws 2 kilowatts of electric power could do. Okay, so you need these components. Okay, this is a 2-ton scroll compressor. $500, glycol to air. This is to basically cool down the air in your house, and this is a circulation pump. Okay, these are the big components. And then you got your tank. Well, can you build? This is off the shelf, right? This is I can go and buy these components, right? And then you have to assemble them, pipe them, and so on. So can you build it for about $1,500? And I would say that at scale, in an industrial manufacturing plant, yeah, you could do it for $1,500. But that's still too expensive, right? Because that's only half the price of your Tesla battery. And so what's happening today is, well, okay, how do you compare it to a Tesla Powerwall battery? Or the equivalent LG or whatever. So we basically have the electric equivalent of 4.2 kilowatts. We have the equivalent of 7 kilowatt hours. We have a lifetime at least 20 years. Easy maintenance, friendly materials. Okay, you don't have to go and dig cobalt out of Central Africa. You can. It's just okay. It's just plastic. scales pretty easily, but you can only use it to cool your house, right? You cannot use it to run your TV or your computer or anything like that. So you still need a battery, right? If you want to have your resilient system, you don't need as big a battery. Okay, to me it doesn't make a whole lot of sense to have very complicated electrochemistry to essentially cool down water or heat up water. Okay. Now, who would buy this thing and why would they buy it? So, a green-minded homeowner would say, okay, well, as a companion to a battery, I want to have my resilient system. I want to, help integrate more renewable power. I want to reduce my demand charges if I have a time of use rate or a real-time price. Utility companies might be able to finance this for their customers, right? Because they're interested. They want to flatten the duck curve. They want to avoid infrastructure upgrades, right? So they can do it by, instead of building more power lines, they just give these devices to their customers. Third parties might want to do this, right? Just like third parties now will put a solar system on your house and charge you a flat rate for electricity for the next 20 years. You can do the same thing, or manufacture of AC systems. In fact, now with more restrictive global warming potential standards for refrigerants, you end up using natural refrigerants like ammonia, like propane, that you are not able to put in a machine that sits inside of your house. So they have to be outside, and to transfer cool to the inside of your house, you have to have a heat exchanger, you have to have a glycol system, you have to have all these things. And so all of a sudden, if you do this, then all you need to do for your thermal storage is basically a box with a bunch of plastic bags, okay? The rest of all the other components are already embedded in your air conditioner, okay? So now the cost goes down from $1,500 to maybe $200, and now it starts being attractive compared to a battery. So I think that's where we're going now. So next steps are going to be build an apparatus and verify predictions. We actually, when I was back at the University of New Mexico, I was doing that. I may actually trying to get some funding to do this at the lab at EPRI in Knoxville. By the way, EPRI has a lab in Knoxville, right? Pretty close to where you guys are. And then optimize. This could be a numerical simulation as well. So we need to optimize the channel size, the ISPAC size, dimensions, and so on, and build and test a prototype. And so at this point, that's it. That's all I got to say for today. So thank you for your attention, and any questions?
Thank you very much, Dr. Andrea Mammoli. It is a great presentation. I really would love to have this if this comes around like $500. So we've got a few questions. The first one is from Dr. Kevin Bai. Let me try to find it. So why don't they combine energy storage with solar? Is Tesla Powerwall the answer? I think you've addressed it. So Dr. Bai, do you have follow-up questions on this?
Yeah, I mean, so the main reason why they don't combine solar with, they're thinking about it. The main reason right now is cost, right? Okay. And again, it's a matter of economics for the customer, for the utilities. The main driver behind people buying battery systems right now is that PG&E oftentimes will cut off power for 1 or 2 or 3 days because it's windy and they're worried about forest fires. That's the main reason why people buy batteries. It's not because of economics, it's because of resilience.
Okay. So the next question is from Thomas. How would California borrow power? Isn't the Western grid interconnected? The
Western grid is interconnected, yeah. So I mean, is that a question related to the the blackouts, the rolling blackouts?
Yeah, I think it was around dark curve or Thomas.
Yeah. So it is interconnected, but I mean, the California system operator still has to balance power within its own boundaries, even though it's interconnected. Transfers of power between states or between authorities, let's say, are still somewhat limited, and they basically want to maintain, if not a balance, at least they want to maintain what they said they were going to buy. So, yeah, but yes, it is interconnected.
Yeah. So, okay, two more questions. One is from Chirath. I'll unmute you and let you ask. Chirath?
All right. Thank you, Dr. Andrea, for the comprehensive presentation. My question is there a less complex power system model that can be used for the TherMech, like using less number of system states, maybe the edge temperature, maybe the...
Well, it depends on the assumptions that you make. I mean, this is already somewhat simplified to what you would have to, basically this is a, so it's one-dimensional in the heat medium, and it's semi-two-dimensional in the freezing, in the phase change material. If you have very thin layers, then you can assume. I mean, this depends on the BO number, right? So if you can assume constant, uniform temperature, so very thin layers, then yes, you can actually just look at the interface temperature and just model the evolution of two temperatures. But as you can see from these simulations, there is definitely a temperature variation in the crust, in the transverse direction. So you kind of have to model that as well. I mean, potentially you could come up with an analytical model for the evolution of temperature in the ice in the transverse direction. So you basically you solve the equations instead of analytically instead of numerically. But I mean, this is actually very inexpensive. It only takes a few seconds to solve several hours of freezing or thawing.
So, what in the current simulation, what is the system state look like? What is the number of dimension?
Good question. I think I have to go back and look, but so you have I think I used 100 nodes in the longitudinal direction and 10 nodes in the transverse direction. So that's basically 1,000. It's 1,000 points. 1,000, let's say, coupled unknowns. Yeah.
And my last question is, how is TherMech compared with phase change building envelope as far as the pros and cons are concerned?
Yeah, so phase change building envelope, so you mean phase change materials in your walls?
Yes.
Well, it's the heat transfer, right? So you're able to control your temperature more effectively. When you have phase change materials in your walls, you need a fairly large temperature difference to get effective heat transfer to and from the walls by several degrees. Whereas with this system, you have much more control on how finely you control the room temperature. That's really the main difference. And it's really an active system instead of a passive system.
Thank you.
We have one last set of questions from Tuhan. So the question is, why people will buy battery banks? Rather, power companies should construct a solar system and battery bank at a massive scale and serve the duck head during evening. Those people will get power and supply company will mitigate excessive demand. And for a massive, sorry.
Yeah, no, sorry, go ahead. Finish your question, sorry.
Oh, yeah, I think it's another comment. So from Tuhan as well. And for a massive scale, utility company will not get such commercial problem as a normal household will face. also government can give subsidy to a utility company for massive scale operations. So what's your comment, Dr. Mammoli?
Yeah, and in fact, they're doing this. I mean, they're kind of approaching the problem from all different sides. So yes, they are building big battery farms in places. So I mean, it's so when you build things at scale, typically they are more inexpensive, and I think that we still have not figured out the optimal. Where should you put the storage? Should you put it at the distribution scale? Should you put a big a giant battery farm in the middle of the desert? Right close to your solar generation station, and and companies are doing that. Right now, so is there a reason for doing it at the distributed scale? But possibly yes. And it's kind of the same reason. It's a resilience aspect as well, right? So if people have batteries at their house, then you have more resilience at the local level. But the question is always cost versus scale, right? So giant battery banks in the desert are more cost effective than individual installations for sure. But so if you do it this way, you to some extent, I mean, if you have a lot of distributed solar, it also makes sense to to reduce the distribution upgrades. It makes sense to also have distributed storage, because basically you remove the need to serve a whole bunch of load when you don't have the solar running, right? So you basically keep the electrons local to some extent. Now, and the reason why thermal is interesting, why thermal storage is interesting as well, is that basically you convert your solar electrons, your distributed solar from your rooftop directly to your ultimate end use, which is thermal, right? So you just shift the time that you use it, but I mean, you're still doing the same conversion, because ultimately, you're running your heat pump or your air conditioner, but instead of running it to meet a thermal load, you run it when you have more power. So but basically you keep the electrons local, but you can do this with a thermal storage potentially in a much more economical way. So I don't know if this answers your question, but yeah, I mean, there is no clear-cut answer. I think it's an optimization, and the optimization depends on ultimately what you want from your system.
Okay. Yep. Doctor, sorry. Tuhin has another, the final comment that says it should be a substation format, as we do serve in today's power distribution system. And well, I agree with Dr. Mammoli's saying that it's basically a balancing the cost and effectiveness. And so if there is no more question, and I think that's
Professor.
Oh,
yeah,
yes.
I have one more question to Professor
Okay.
Mammoli.
Last question. Okay.
Yeah. So suppose I have installed that component in my house, and suppose today I made the ice, everything ready, but I have gone for vacation for 7 days. And after 7 days, when I'm coming at the evening or maybe at the daytime, I need to use it. So I need to keep my all components always running, because the ice will be otherwise will be, again come to water. So in that way, that means whenever I'm staying there, it is good. But when I'm coming intermittently, I'm not benefited. That's what I feel.
Well, okay, so that's a good question. But so let's assume that you you have a photovoltaic system on your roof, or not. But so I mean, when you're away, you can control these things remotely, right? I mean, just like you would do with your house thermostat. right? So you can either control them remotely, or you can program them, or there's some kind of AI like in your Nest thermostat that learns that you're not at home, so hey, I'm not going to store. There's nobody home, right? So I think you basically just you integrate it with your existing smart home devices, and yeah, of course, you're not going to charge it and discharge it if you don't need it, but you just sell the electricity back to the grid, or not use it. So, but I mean, it can be controlled remotely, just like any other Internet of Things device can be controlled.
But I will have some expenses on that. So that is what my point. Say, like how to minimize my expenses, because as a normal household, my target will be, my expenses will be lesser. So in that case.
You mean your capital expenses?
Yeah, means like this is also as a budget. Like I need to keep.
Okay. So I mean, if you're saying if this is a second home and you're not there all the time.
Yeah, that's the thing.
Yeah. So again, you've got, yes, you definitely have to look at the economics. So it doesn't necessarily make sense economically in all circumstances. Only, if again, just like any other capital piece of equipment, whether it's owned by you or the utility company, utilization, the capacity factor is important. So yeah, if you're only going to use it occasionally, probably not worth installing it.
Yeah, but if suppose there is a big house where at least 5 or 6 houses, or maybe it's like a flat structure where always somebody will be there, it will be.
Well, yeah, definitely. I mean, yeah, and this actually scales up pretty well. So yes, this it makes sense to do this, and on top of that, there are also optimization algorithms that allow you to figure out when you design such a structure. Let's say you're building a block of apartments. You can run, you can get these tools from NREL, for example, to optimize the size of an electric battery, right? If you're building a house, they'll tell you what's the optimal size of your battery. So, you can use similar tools. I don't know that they exist, but they should, for thermal systems. So, yeah.
Yep. Thanks everyone for asking questions. And if our audience have more questions, I would encourage you to take the discussion offline and continue it. So again, thank you, Dr. Andrea Mammoli, for coming to CURENT virtually. Quote, Dr. Chen is saying. So please come visit CURENT in Knoxville again. And thank you for the great presentation.
All right.
Yeah, next time I'm sure you will come to EPRI in Knoxville, so don't forget.
I will definitely come, and yeah, we'll go and have a drink for sure.
Yes, we'll have a drink. Yeah.
All right.
All right. Thank you so much.
Thank you.
Thank you, and goodbye.
Okay, thanks for the invite, and yeah, I enjoyed the questions. So yeah.
This is one of our most popular ones.
Great.
Thank you. Take care. Bye-bye.
All right.
Take care.
Bye-bye.
Bye.
Bye.